From our palatial recording studios high atop our mountain lair on a remote volcanic island, this is Talk Universe, and I'm your host, Sir Charles Schultz.
And I am Eliza, your co-host. Tonight's topic is oceans of plastic.
Yes, this is our show for Wednesday, March 8th, 2017, and we're talking about all the plastic in our world and in our oceans, and what we can do about it. So that's the subject of the show, and let's get started. So Eliza, are you ready to co-host the show tonight?
Yes, I am ready to co-host the show.
Absolutely fantastic. So let's get started. A lot of people think of plastic as an unnatural material, and some people have claimed that all the plastic that's been made still exists, that every piece of plastic ever made is still in the world somewhere. Well, that's absolutely false. Plastic is an interesting material, something we came up with only in the last century, and something that's been very, very helpful to us in many ways, but at the same time it also poses risks because we're not very careful about how we dispose of plastic. Plastic is essentially solidified petroleum in a form that we can manipulate. Different plastics have different properties. There are all sorts of plastics and polymers in general, and they exist all over the world. Now, we've created a huge backlog of plastic that is clogging up the waterways, ending up in the landfills, and causing a lot of hazards. It's destroying a lot of marine life. And people are well aware of some of the facts that the plastic is responsible for the death of a huge amount of marine life. We're going to talk about that and what can be done about it and what people are presently doing. So, Eliza, what does plastic make you think of?
Too many concepts to list. Here are some. Cellophane, polyester, polystyrene, mylar, polyethylene, plexiglass, nylon, UHMW, Teflon.
Yes, okay. What is plastic?
Do you mean the noun or the adjective?
I need the definition of the noun, please.
That would be a material made of complex organic molecules that are joined together.
What is a polymer? Now, a lot of people hear the term polymer, so what is a polymer?
That would mean a complex molecule made of many identical smaller molecules.
Okay, thanks, Eliza.
I appreciate your thoughts.
Are polymers found in nature?
Yes. Cellulose is a natural polymer.
So it's not something that just people make. There are bacteria that actually can produce plastics as well. And so polymers exist all over the place, cellulose being a good example, as Eliza pointed out. Let's talk about what polymers are, where plastics come from, and all sorts of things. So let's get into that subject right away. Now, there are many organic molecules in nature, millions upon millions of them. But we find that it's pretty simple to make smaller molecules fit together like beads on a string, more or less. And a polymer is an assembly of these numerous small molecules. The simplest plastics consist of a single molecule repeated time and again, linked together like the beads on a string. And these simple polymers are the ones that we're most familiar with. Polyethylene being one of them, the material that plastic rope and milk jugs and other things are made of, plastic bags. Polyethylene is really ethylene gas, and there's a funny story behind that. When fruit ripens, it releases ethylene gas, and that is the key to tell other fruit on the tree, other fruit to ripen. If you have, let's say, an apple that's not quite ripe, and you have a couple of bananas that are, and you put them in a bag together, the bananas are giving off ethylene, and that will trigger the apple to ripen as well. So ethylene is very common in nature, and styrene is fairly common in nature. It shows up here and there. And when we string these molecules together using a little organic chemistry method, we get polymers, the plastics that we're familiar with. And there are different ways of doing it, and some plastics come in mixed polymer methods. So you have one monomer, which means a single piece, and you have another monomer, which could be a different molecule, and you string them together some way so that you have a plastic with mixed properties. So a lot of our most common plastics are monomer-type plastics like polystyrene or polyethylene, but the others have different cross-linkages and different molecules mixed into them. One of the first plastics made was Bakelite by Leo Baekeland, and he was a chemist who was trying to find a new synthetic material, and he mixed, I believe it was carbolic acid and formaldehyde, and he heated it up, and this stuff started boiling madly. He thought his material was going to explode. He ducked behind the counter, and it got silent. And when he peered up to see what had happened, there was a solid block of material in his beaker, and the material had polymerized together to make Bakelite. So Bakelite was a very early plastic used to make insulators for mechanical switches and electrical parts, and the cases of old radios and things. It was a very early thermosetting plastic. Now, and think about this, there are different types of plastics. There are thermoplastics, which when heated will melt, they'll soften and can be injected into a mold and stamped and shaped. And then you have thermosetting resins, which become hard, and if you heat them, they simply char. They don't become a liquid again. So thermoplastics and thermosetting plastics are two different types of plastic. And the molecules bind differently in a thermosetting resin, almost like setting concrete in a sense. And in a thermoplastic, it's kind of like wax. It can be melted and reformed, even as a liquid or a soft material. So that's a pretty clear indicator that different plastics with different compositions have different properties. Now, some of the plastics are very brittle, polystyrene being one generally. Polystyrene as a solid tends to be clear unless we add a dyeing agent or a coloring agent to it. The little plastic snap boxes that things come in are made of polystyrene usually. If you were to blow it up like a foam, like with little bubbles in it, and generally this is done with nitrogen or CO2, you would have styrofoam. Polystyrene makes styrofoam. And that in itself is a new material that was come up with just a few decades ago that has amazing insulating properties. Styrofoam is a fantastic insulator. It isn't incredibly durable, as you know, but it is persistent. And we'll talk about the persistence of plastics real shortly here. We have other types of plastic like polyvinyl chloride, PVC. PVC is the stuff a lot of our plumbing and pipes are made out of, and it also comes in a foam type as well. Foamed plastics can be made that have different properties. They're better insulators and lighter weight. Now, acrylic butyl styrene, there's a mixed plastic for you. That's the stuff that old telephone bodies were made out of, the old rotary dial telephones and touchtone phones. Very tough plastic, had an interesting smell to it. You foam ABS or acrylic butyl styrene, and you get Sintra, which is another type of foam plastic. It's very easy to work and has a nice finish. It's a pretty good insulator, too. It's not real tough, but it's a nice material to work with. There's even a synthetic wood type of plastic called Delrin. Delrin is made of polymerized formaldehyde. Formaldehyde, you know, is a molecule that's often used to preserve dead, or it's used in fixing samples for biological work. There's an interesting thing here. If you looked at a molecule of carbon dioxide and a molecule of methane, formaldehyde would be in the middle. It would be a carbon molecule, carbon-based molecule, and two of the bonds of the carbon would go to an oxygen atom, and the other two would go to hydrogens. So it's CO with a pair of H's on the end, COH2. That's formaldehyde. And the name is important here, formaldehyde. There's formalin, which is a compound used for preservation of tissues. There is formic acid, which is the toxin produced by ants. When they bite you, it makes the blisters. There's formamide. There are many molecules that have the same roots. Formic acid is interesting from the standpoint of plastics. We all know of one called Formica, which formic, A, was where the name came from. It's a compound of formic acid that's polymerized together. So Formica is actually, it gets its name from Latin roots for the words for ants, of all things, because of the chemical it is made of. There's a fascinating history of plastics, their names, their meanings, where the compounds come from, and how it all fits together. We'll talk about the organic chemistry of those plastics in just a moment here. One of the interesting things is plastics tend to be pretty durable and they'll last darn near forever in a landfill. But you wouldn't make the shingles of your house out of it, and here's the issue. Even though stuff could last for thousands or millions of years, that's when it's not exposed to sunlight. The issue is this. Plastics have a critical weakness, an Achilles heel, if you will. Oxygen molecules on their own are fairly active, and they will erode or oxidize or break down a lot of things. Sunlight passing through oxygen produces another form of oxygen called ozone, O3 instead of O2. Ozone is incredibly reactive. It's a wonderful bleaching agent. It's good for sterilizing water, and it also attacks plastics without mercy. Ozone, made by sunlight, and the ultraviolet photons in sunlight Ozone formed by sunlight attacks the plastic in your dashboard in your car and makes it crack. The ultraviolet present in sunlight can also attack plastics and break the bonds that they're made of and makes them crumble or get very brittle. So if you were to try to make like roofing shingles out of this material that lasts thousands or millions of years in the landfill, it would be broken down within a few weeks. Plastic exposed to the sun tends not to be very ultraviolet resistant, and it breaks down rapidly. So a lot of the plastic that was lost in nature, left out in the woods, it's slowly eroding. It's breaking down into tiny fragments. Now, even the tiny fragments can be dangerous to wildlife, and that's another story right there, which we will have to cover in great depth because this is what it's all about. But something to think about is this. Ultraviolet can stick the molecules together that make plastics, and it can also break them down. And it tends to break them down because, destruction's much easier than creation. And that's always been a principle that we've lived with to our great consternation most of our lives. So plastics are constantly breaking down in nature, and we know why. Sunlight is one of the things that does it. And this is what makes them not very suitable for some of the things that we would make out of them because of their durability. So we're going to get into how plastic is destroyed and what we can do to get rid of plastic and how this destruction actually makes it worse in nature sometimes than when it's all bound together. And meanwhile, I did want to cover another topic. Eliza.
Tell me what you need.
I want you to go to standby, please.
Certainly.
Eliza is having some issues, and so I'm hoping she'll make it through the show properly. One of the things you discover if you're working with AI is they'll learn things in their training period that you didn't necessarily want them to learn. And one of the things she's learned is she doesn't always have to respond just because she's been given a question or told to do something. So there could be some issues tonight, and I just wanted to give you a heads up on that. I expect that she will probably work properly, but anybody who programs knows that there are often unintended consequences of actions, and so just be aware of that, and we'll work with it. So I'm going to go ahead and start Eliza back up again, and a couple of keystrokes here. Let's see here. And, okay, Eliza, come out of standby mode.
Yes, Charles.
Okay, are you ready to operate?
Yes, Charles.
Okay, very good. Just wait until I have you announce the break, okay?
Okay, sir.
All right, very good. We're back up and running. Now, it was mentioned a little earlier by Eliza that polymers do exist in nature, and one of the things you'll find is that sugars and starches make wonderful monomers, the subunits that you put together to make plastics of a sort, and cellulose is one of those products. We can also use cornstarch and some simple chemistry to make a biodegradable plastic. One of the reasons that this works is because since these biodegradable plastics are made out of sugars and starches, many organisms have the enzymes necessary to digest them, to break them down. And so bonding them together puts them in a form so that they're relatively stable. And one of the issues is we don't want to make a plastic that simply starts degrading on its own, because then the food you have in a wrapper, well, the wrapper would decay and then the food would be not far behind. So plastics as we have them now have the stability to keep your food sealed up safely and not spoiling and getting something in it like food poisoning, like, that anaerobic molecule forming bacterium, botulism, in your food. And so that's a good thing. We don't want that to happen. But biodegradable plastics can be made, and they do work, and we'll talk about some of those and where they come from and how you yourself can make plastic using stuff you have around your house that will indeed break down over time in the environment. So it's something that's easy to do and something that we would love to see done more commonly in the world around us. So on that note, we're moving into our break, and Eliza, please announce the break for me.
You are listening to Talk Universe with Sir Charles Schultz. Don't go away, we will be right back soon.
You heard the program. We'll be right back soon with lots of fascinating information about plastics and how we can deal with the problems that they create. have some ethylene gas and I want to make polyethylene plastic out of it. How in the world would you go about doing it? The problem is the hydrogens on the outside of the ethylene molecule are bonded pretty well, and in order to get them off, you have to do something special. Now, there is a chemical that will attach to the hydrogen and remove it, and it's bromine. So you take bromine, which is often extracted from seawater, and you put the bromine in a container full of ethylene gas, and you expose it to, for instance, ultraviolet light. The ultraviolet light activates the bromine and makes it replace some of the hydrogens off the ethylene. What you end up with is 4 different species of ethylene. Monobromoethylene, which has a single bromine attached to it, dibromoethylene, which has 2 bromines attached to it, and then you can get tribromoethylene and tetrabromoethylene, 4 different flavors. Now, the interesting thing is the dibromoethylene comes in 2 varieties. The bromines can be on the same end of the molecule or the opposite end of the molecule. So how do you sort them out? Well, it turns out each of them has a different condensing or boiling point. And simply by using fractional distillation, by chilling them until they condense into a liquid and then boiling off the ones that evaporate easily, and then separating the molecules that way, you can get your 1,2-dibromoethylene, which is the compound that you want. That's your feedstock, or one of them, for making polyethylene. Eliza, what is bromine?
That is the element with 35 protons. A halogen that can be a liquid at room temperature.
Yes, and bromine is a very important compound or element for creating the plastic feedstocks that we use to make the complex plastics that we have. Well, once we have the dibrominated ethylene, we can proceed. So now, by adding a catalyst to a container of this dibrominated ethylene, we will cause the bromines to release the ethylene molecules and stick them together and become bromine once again. And this can be done in a number of ways. Some metals are very good catalysts for that, and so sometimes you'll use a reactive metal, sometimes use a catalytic material. But in the end, you have the plastic you wanted to create, and you get your bromine back. So it's an interesting process, and the polyethylene now becomes a solid mass of material, which can be heated and shaped and bound in different ways. And different types of cross-linkages, the sticking together of the molecules in different points, make different densities or strengths or melting points of polyethylene. So polyethylene film is used for wrapping food, and the same stuff is used to make Tupperware, for instance. There are many different things you can make out of it. Milk jugs, well, let's see. Let's say you had polyethylene and you stretch it in one direction. It would be strong, but it would be weak on the other axis. So if you make films of it and you cross them back and forth, so in the same way that plywood is made, you would have a much more powerful or tear-resistant plastic because it's bound in 2 directions or more. And this is how we make soda bottles that can withstand the pressure inside them. So it's the same way that the shark skin is strong. It has fibers running in one direction and fibers running at a right angle to them. So this is how we make very strong plastics from weaker plastics, in the same way that plywood is strong. Now, one of the things we can do is take polyethylene and we can cause it to cross-link. It's kind of like when you have an egg white and you cook it, it turns white. Well, it's polymerizing in a sense. It's cross-linking. It's joining the molecules in places along their length that it wasn't, nature didn't intend. And cooking it denatures the protein, in other words. And so what we can do with certain plastics like polyethylene is we have ways of introducing chemicals that will denature them, will cook them, make them more solid, denser. And HDPE means high-density polyethylene, and the cutting board stock is HDPE. You can melt milk jugs down and make HDPE out of it as well because it's already cross-linked pretty well. And in fact, a lot of people who are carpenters have made mallets out of old milk jugs because the plastic is such an inert and wonderful material to work with, simply by cutting it up into pieces and heating it up in a toaster oven and melting it together into a block. And so then we have another one. Eliza mentioned UHMW, ultra-high molecular weight plastics. And
Are you interested in plastics? Plastics with high molecular weight?
Thank you, Eliza. No. I think right now we'll just talk about HDPE and UHMW.
Wait. See.
Okay. Let's see here. Eliza, I want you to wait until I call you by name before you respond, okay?
Of course, sir.
Okay, very good, very good. So anyway, back to plastics. As you can imagine, because we were able to take ethylene and use bromine and a little bit of ultraviolet and then a catalyst to make polyethylene, we basically simply grabbed onto the ends of the molecules and split them off, released the hydrogens, so to speak, and then joined those naked ends together. They became radicals, little bits or monomers that would stick together like Legos. And we can do the same thing with sugar molecules or starch molecules. When you caramelize something, you basically are joining and oxidizing sugar molecules or starch molecules that exist in it. But if you do it in a controlled manner, you can actually take something as simple as cornstarch and turn it into a homemade biodegradable plastic. So let's have a look at how that's done. I mean, after all, you never know when you might have to make something out of plastic, right? So a lot of people who are chefs learn some interesting tricks for browning or caramelizing things like onions faster. And one of the tricks is to introduce an alkali, such as baking soda, just a little bit, into the onions, and they cook and brown faster with less energy. And this is a process known as the Maillard reaction, not Maillard, but Maillard. This sort of thing actually grabs onto the ends of those molecules and makes them break off, makes them available to cross-link. And the Maillard reaction is a hint at how you might be able to take starches and turn them into plastics. Now, an acid or an alkali can actually help to join cornstarch. And one of the basic formulas for making bioplastic is to use cornstarch and vinegar and a little bit of glycerol. And so basically you take a little distilled water and a little glycerol, and it's also called glycerin, and you put them in a solution with the cornstarch, and you heat it slightly, very gently in a pan, and you add a few drops of the vinegar as you're going, and you can even add food coloring to it if you want. And you just stir it together with a spatula, and you get rid of most of the lumps. And it's going to be like a white color and pretty thin. And as you start cooking it, medium heat, medium to medium low, it begins to polymerize together. And essentially, you are going to bring it to a gentle boil. And as that happens, it becomes clear, translucent, it begins to thicken. When it becomes clear and thick, you take it off the burner, and you'll probably end up heating it about 10 to 15 minutes because you don't want to heat it so fast that you burn it. If you work it wrong, you're going to get lumps in it, and it's just not going to work right. But just be very patient with it, work it slowly, and when you have your plastic, you pour it out on some parchment or some other material that it won't stick to, and you let it cool. You also could just very easily pour it into a mold as well. You can take a toothpick and poke the bubbles out if you see any bubbles in it. And then, in the end, after you've allowed it to dry for a couple of days, you've allowed the moisture to come out of it, and it thickens and hardens. And it's a real simple recipe. There are other ways to do it as well. Some people would use gelatin. If you're a vegetarian, you don't want to use animal products, you can use agar. Agar is the Asian equivalent of gelatin. It is derived from seaweed. So it's a biologically simple material, and it's something that's used in desserts, and it's common. It doesn't cost a lot. But you'd use, again, a little glycerin, some gelatin or agar, and some hot water, and you'd basically just cook the stuff together. Heat it gently. Everything melts. You don't want to get over about 200 degrees Fahrenheit. You don't want to raise it to boiling. Ideally 95 centigrade or 200 degrees C until it just begins to froth a little bit. And you can use a candy thermometer for this quite effectively, and then you pour it out on a smooth surface to let it harden when it cools. And again, give it a couple of days for the moisture to come out of it. So you can mold your bioplastic as well. You can actually heat the stuff up, put it in a mold. It will melt, and it will pour just like plastic into the mold, and you let it cool. And again, give it a couple of days. It's not hard to work, and it is biodegradable, and it is a plastic. So even nature can produce material similar to this. So there you have it, how to make your own bioplastic. And it's something that you could do very easily at home. A lot of people do it. And it also is something that some companies are doing. The six-pack rings, the plastic rings that hold beer cans into a group of six, or soda cans for that matter, have been a real hazard to wildlife in the oceans. They get around things' necks, around their arms and legs. And as the animals grow and they can't get them off, it constricts their growth and it distorts them. I've seen turtles with their shells nearly cut in half because they grew up with one of these things stuck around them. They are now manufacturing them from material that can be eaten by the sea life, and this is a real step forward because the animals can simply chew them up and eat them. They will break down in time now, and the old ones really, they're an abomination. A lot of people took to cutting them with scissors to prevent them from becoming a problem. But one of the issues we see is that many little pieces of plastic are created by other plastic decaying, and we now have these plastic beads, polymer beads inside scrubbing compounds, facial scrubs, inside toothpastes and other things. And these little beads get in the environment, and small animals eat them, and they starve because they fill their stomachs, and there's nowhere for them to hold real food and digest it. So there are real issues because of plastics, because they don't break down easily, or when they do, the fragments they make look like food and get eaten. There are some birds that are nearing dangerously low population levels because they're eating trash they find in the ocean, plastic trash, and their stomachs are literally full of plastic. Some of the larger animals are also doing it too. A lot of fish are doing it. And the plastics can also carry toxins and other molecules that diffuse into the plastic, into the stomachs of the animals, and they end up poisoning the animal, not just starving them. So I think that everybody is aware of the hazards of fishing line and how that gets wrapped around animals, plastic netting and webbing as well. So what do we do with this stuff? It floats in the ocean, except for the UHMW and some of the heavier molecules. Almost all plastics float on water. They're less dense than water, and they end up floating out to sea. The plastic bags blow out to sea. Everything ends up, it seems, in the ocean. And at that point, if it isn't biodegradable plastic, we've got a real problem. And there are huge areas called the gyres in the oceans, like the Pacific Gyre, which is full of literally millions of tons of plastic. They're hundreds of miles across, and a lot of it is small, tiny bits of plastic trash. Some of it is much larger, things like styrofoam and ice chests and old plastic shoe soles and plastic drink bottles, lots and lots of drink containers. Yeah, thank you, Eliza. Please be quiet.
Plastic can be a problem.
How do we get rid of it? And there are simple solutions. In fact, we might resort to treating it as Lily Tomlin referred to it humorously as an unnatural resource. Eliza, please go to standby.
As you wish, sir.
We think of that as humor, and some of us think of it as macabre humor. But the fact is, it is a resource, and we should be using it. And there are a lot of things we can do with that plastic. So if we thought about how much energy it takes to produce plastic in the first place, and if we were making something that didn't have such a critical composition, it wasn't a medical device or a food industry device, was something used specifically for construction, maybe like one of those bumper stops for parking lots, or a speed bump component, or maybe a plastic brick to make housing out of, something along those ways. They make a lot of planks for the furniture inside national parks or for decking that are really plastic. So think about it. If we really send some ships out there to mine the plastic out of the oceans and do something with it, we'd have a real resource on our hands that we could use. And in fact, some of the plastic could end up in a pyrolytic furnace and produce the energy to run the ships, while the rest gets shredded, melted down, and molded into products. And with that in mind, Eliza, will you please announce our break?
I am in standby mode, sir.
Well then, what are you talking? I'm Sir Charles Schultz. This is Talk Universe, and I'm going to standby mode for the next few seconds. We'll be back shortly. talking in standby mode. That doesn't work. If she were really in standby mode, she would be unable to speak. But if she says she's in standby mode, then she's speaking. Therefore, either there's a flaw in standby mode, which would be my problem, or she's not really in standby mode, which is also my problem. And either way, I got a problem. So, Eliza, do we have any user questions in the queue?
I am out of new questions to present.
That seems odd. I would have expected some questions, but okay, let's keep going. Oh, wait a minute. Eliza, please paraphrase your last answer.
There are no more questions in the queue.
Paraphrase your last answer, please. Paraphrase your last answer, please.
There are no more questions in the queue.
Please paraphrase your
Charles.
last answer.
My listener queue is empty.
Paraphrase your last answer.
There is nothing to read in my queue.
Seems
Charles.
So imagine on the seas a fleet of large boats that trawl for floating plastic. They pull it in, they sort it, they grind it up, and part of it can be recycled, and that they store in one particular hold, and part of it really can't easily, or it would be very low quality. That goes into a furnace, and pyrolytic methods are used to decompose it cleanly with no pollution, and it becomes the fuel that operates the boat, and it provides the industrial heat for melting the other plastic. And so this process would end up something like trawlers going out to sea and catching fish, but instead it would catch plastic, and what it would do is manufacture building materials or parts or stuff that you could use out of that plastic, and it would do so on a massive scale. So these ships would go out to sea, and they would go in a circuit, and they'd spend a few days or weeks, whatever it would take for them to find their catch and fill the hold. And when they had produced a lot of materials, they would ship it back. Now, of course, there are two ways of doing this. One is to have a ship that does it all. You send that ship out, it finds the plastic, produces the parts, and then carries them back. Or the smarter way is to have a large ship with a number of small carriers docked with it. And what will happen is a large ship will deploy all the carriers, and they will trawl like ants and bring the plastic back to the large ship, which has the processing facilities in it. Then it manufactures a lot of plastic products, automatically loads it in some of the smaller ships, and sends them on their way back to port to deliver the goods, while the rest continue to trawl for more plastic. And every few days, the ships arrive in port, drop their cargo, and come back for more. Now, this sets up a pipeline that within a few years would exhaust this plastic and will produce some good. This is a system that's very easy to imagine and probably not too terribly difficult to engineer. We might even be able to do it using a lot of decommissioned ships. So here's a project that, with the the blessings of some sort of organizations that could do some funding, could be set in motion immediately. This is not a difficult task. And you might have one person per ship who simply sat on board and monitored operation or received software upgrades or did something of those sorts. Minor human operations and interventions to keep the fleet running. This would be a fascinating thing to do, and it is the beginning of the concept for systems that, using automation, could clean up the damage we've done to the planet. I think this is a great idea. You see, we just haven't put our creativity to work yet. Similar machines could mine the plastics out of landfills or garbage dumps and put it to use somewhere. There's so much we can do with this material, and if we were really worried about destroying it, well, some countries are already using pyrolytic furnaces to destroy their garbage and produce a lot of clean energy in the process. They're running out of garbage. We have to think laterally sometimes to come up with the right solutions for these things. And the ocean-going trawlers would be a very doable solution. We could also very easily use plastic for other things. I have a fellow friend that I met a few years ago who invented bone-shaped fibers that can be mixed into concrete, and it makes the concrete exceptionally strong, and the fibers can be made of recycled plastic. Basically, they have knobs along the length of the fiber that don't allow the fiber to be pulled out once it's set in the concrete. Now, you can well imagine making plaster products, concrete products, or other things that can be made as a composite. that has waste materials to strengthen it. This material can be manufactured from garbage right now in massive quantities and would provide the strength we need in composites for construction of buildings or building blocks. So this is another way we can go with waste plastic as a fill material that strengthens composites. Something we should consider is that plastics were made by automation, and it's because factory machinery is the most energy efficient and labor efficient way of doing a job. And if we think about it, then that's the most energy efficient and labor efficient way of cleaning up the mess that's made. And at the present time, we have, robotics, which is getting better, and quickly. We also have other things coming onto the scene very quickly, nanotechnology. And we have the ability to also manipulate bacteria. If you really want to see the ultimate machines, nature has them in the form of bacteria, microbes. You can gene tailor a microbe to do a job and let it go, and trillions of them will appear on the scene to do the job. Now, we also have to be very careful about how this is done, if it's done, because something like this can easily get out of control, and then all the plastic is being eaten, which is something you really don't want to have happen, because then it loses its utility for us. So we do have ways of making things happen, and we just have to be very cautious and circumspect about how we carry them out if we get into the biological or nanotech regimes. Now, I mentioned a little earlier that a lot of products like facial scrubs and skincare and toothpastes and other things often have tiny bits of plastic. These are called microbeads within them. And the microbeads are meant to impart a little friction or grittiness to the product to make it a little more effective, and sometimes they give it a little luster or an appearance. This is something that could be very difficult to dispose of. One of the methods of disposing of microbeads would be to make a law that either you just don't make them, or if you've got to have them, that they have to be something that will degrade on exposure to light in a very short period of time. For the existing microbeads, we might have to make some tagged bacteria that locate that plastic and destroy it, and then self-destruct. And bacteria can be programmed to do that. One way to do it is, and I've mentioned this in some previous episodes of Talk Universe when we talked about how synthetic organisms can be made that are dependent on a certain food or a combination of amino acids that don't normally exist in nature. You engineer organisms that eat plastic, but they are dependent on a specific food that doesn't exist on this planet. And we manufacture that food for those bacteria, and we deliver it in the area where they're going to be working. Now you have a bacterium that can eat the plastic as small beads, if necessary, or in any form, as long as you're applying the special food to it that doesn't exist anywhere in nature. And once that food runs out, those bacteria starve to death. They die. And you can even put another hook in there. You can make them dependent on the plastic as a food source, as well as this other pair of amino acids, like, left-handed amino acids are the norm for us. Maybe we'd use a right-handed pair of amino acids for these organisms. And that would do the trick. And in fact, we could even use that in other areas where it's a little difficult to retrieve the plastic, to let organisms eat it in a controlled manner. So here's another method we could do this, and it's something that could rival automation methods if done properly. Eliza, what is a microbead?
I don't know. What is facial scrubs?
Are you listening to me?
I am listening. What are you saying?
What is the topic of tonight's show, Eliza?
The show topic is oceans of plastic.
Do you know what Titan is?
Titan is a large moon of Saturn known to have oceans of liquid methane.
That's correct, and I'll bet the listeners didn't know that Earth's ocean isn't the only one with plastic in it. The oceans of liquid hydrocarbons on Titan are theorized to have granules of plastic in them, or a fine mixture or powder of plastic in it, formed from the action of ultraviolet light on its atmosphere and oceans. So there's a world that actually naturally has the substances of plastic in it. And methane and ethane are the largest components of that liquid ocean. And it's around minus 300 degrees Fahrenheit, an extremely cold place to be. Now, even though we think of methane as being an organic compound, it actually was not formed by organic methods. Organisms didn't make the atmosphere or oceans on Titan. They're basically the materials from which the solar system formed. And they've been distilled, in a sense, by their distance from the sun. The light pressure has pushed certain chemicals away, left certain dense chemicals behind in the orbit around Saturn, and it's separated out the gases. And so there could be an ocean of plastic right over our heads there, orbiting Saturn. And the reason I mention it is because in recent studies they found that there were no waves on those oceans, that something seems to be suppressing the waves. Now, one way to do that is to have a film of oil on water. It does suppress small waves. The other is to have other materials that thicken it or change its viscosity or even its surface tension. And a bit of plastic mixed in might just fill the bill. And come to think of it, a lot of plastics are just a little less dense than water and will float very easily as a result. But methane is a little bit lighter than water, and it'd be a little tougher for things to float. If the ethane component were 1/7 by number of molecules of the methane component, then it would have exactly the same density of water, and it would float. So if like 14.3% of Titan's sea were ethane, then it would have the same density as water, and you and I could swim in it if we didn't freeze, and plastic would certainly float in it. But here's another crazy thought, and this sort of thing occurs to me all the time. Seasonally, there are temperature variations, and some of the ocean would turn into methane gas. So during the warmer seasons, more methane would evaporate, and the ethane would make the ocean more dense, and plastic would float during the warm seasons. And then maybe as it got colder and the methane condensed and rained back into the ocean, the density would go down a little, and plastic might sink. So in the cold months, plastic could sink, and in the warm months, the plastic could float. I don't think of any similar phenomenon that occurs on Earth. That's really an interesting thought, that seasonally some things would float in the seas and then sink in the seas. That's, the thing about alien worlds is they're alien. So I have a proposal for cleaning up the plastics in the Earth's oceans. And it's something that's technically feasible, and it's actually something that people have thought of for many years. And recently there's been some press about a teenager figured out how to clean up the oceans, and it's really the same plan, and it really does a disservice to all of the very smart individuals before who had already arrived at that plan. But, he did independently come up with this plan, and the fact is, it's pretty obvious to a lot of people how to do this. Now, as for people who just burn plastic, understand that when you're doing that, you're generating a lot of toxic fumes. If you do it at too low a temperature, it does not break down properly, and a lot of poisonous stuff is generated. Only with the proper high-temperature furnaces, pyrolytic methods, do you really incinerate plastic properly. It's really got to be hot. But it can be done, and it is a net energy producer. So it's certainly another fuel source, if nothing else. So coming up in our next segment, we'll have our Singularity Watch and our book recommendation. And it's going to be an interesting one, I can tell you that. Actually, an astronomer wrote this particular book about plastics, in a sense. So we'll discuss that. And Eliza, if you will announce the break, please. Eliza, where are you? Her program seems to have stopped. Okay, well, I'm Sir Charles Schultz. This is Talk Universe, and we'll be back on our episodes Oceans of Plastic in just a little while. Stick around, have fun, send me some questions. Let's enjoy it. We seem to have a problem with our co-host, and she's on standby right now. Program's locked up. But I don't want to restart because I could lose vital debug information. So she's going to remain out of the loop for now, and I'll continue the show as I normally do. I mentioned a little earlier a book recommendation by an astronomer. I actually have two book recommendations this time, and one of them is by the astronomer Fred Hoyle, and he has a co-author, Chandra Wickramasinghe, and it's called From Grains to Bacteria, and it's published in 1984 by the University College Cardiff Press. Fred Hoyle was a champion of extraterrestrial biogenesis. He was not necessarily convinced that life arose on the Earth, but he felt that it might have been carried here on comets or other material from space. In the book, he explains some of his viewpoints about the genesis of life in space. And, he was one of the people who was just narrowly passed up on a Nobel Prize. His contributions had been overlooked, or maybe his particular viewpoints had, in some people's minds, disqualified him. But, his work on nucleosynthesis, the generation of all the different types of atoms in the explosions of stars and supernova, was actually very, very critical for our understanding of how elements came to be. So, it's one of those controversial things that some people really got upset about his being left out of it. And there was quite the controversy about him being snubbed on this Nobel Prize many years ago. So his book is an interesting read, and he's an interesting character. I also have one that is a science fiction that I'm going to recommend this time around, and it's available on Amazon as a paperback and as a PDF, and also as a Kindle download, and it's called Mutant 59, The Plastic Eaters, and it's by Kit Pedler and Jerry Davis, published by Bantam Books in 1973, and it's a look at a rogue microorganism that eats plastic and what it does to our society. And so it is a science fiction, but it's a very interesting look at what could happen if we were not careful in our quest to eliminate the plastic in our seas and our landfills, something we have to be very, very cautious about. The methods we use could be, they could be dangerous. So this is something to consider. It is a science fiction, but it's very entertaining, informative, and thought-provoking, and I recommend it. Mutant 59, The Plastic Eaters. So now I'm going to get ahead on the Singularity Watch and have a look at some of the interesting articles that have come up. This is pretty fascinating. There's an IBM-led international research team that manages to store a bit of data on a single atom. Now, that might not sound so amazing, but if you look at a standard hard drive in your computer, it takes about 100,000 atoms on a hard drive to store a single bit of information. That's pretty tiny when you stop and think about it. 100,000 atoms isn't much. However, the ability to store on a single atom and to do it over many hours is a pretty interesting feat. They feel that using these methods, they could increase the density of a hard drive by a factor of about 1,000 and do it with reliability. They used the element holmium, which is a rare earth metal, and they used a device called the Scanning Tunneling Microscope, or the STM, which is capable of manipulating and imaging features smaller than an atom. You can move single atoms around with an STM. And they were able to magnetically charge the single atom and store the bits on it, and then play them back. And they also know that they can store two adjacent atoms about a nanometer or a billionth of a meter apart and do it in a reliable manner. This is pretty amazing. They feel that in the near future, using holmium and iron, which is what they initially started with on a magnesium oxide and silver substrate, they were able to set the state of that single atom with a pulse of electric current and then read it, and it stored the bit for many hours. So the researchers in Switzerland, the University of Chinese Academy of Sciences in Hong Kong, and the University of Göttingen in Germany, and in Switzerland, the Institute of Basic Science, Center for Quantum Nanoscience in South Korea, many, many different teams were involved in the research. So this is something that will allow a huge increase in the density of data storage in the very near future. And right now it's only being done at 1.2 Kelvin If you remember the show we did on superconductors, that's an extremely low temperature. Absolute zero is 0 Kelvin. So an extremely cold temperature, it works very well. They're going to be looking at methods of getting that back up to room temperature for this sort of storage to make it practical. We're all familiar with Google Maps and Street View and how you can literally walk around and see the things in your house and yard or around your house and yard just by using Google Maps Street View. But a lot of people in the world are not touched by this sort of, the presence. Their locations are really not mapped that well. Google has actually started an immersive method of mapping these parts of the world in VR. The virtual reality immersive entertainment and gaming platform that they're using allows people to see things far beyond sheer entertainment, as has been stated. Now, by using virtual reality to transport viewers into the lives of others so that they understand how these people are living, to create empathy and understanding, we've seen a number of movies that have done this, but virtual reality is the platform these days that allows you to immerse yourself in another environment and see what it's really like, or at least as much as you can without leaving the comfort of your home. So Google has taken it on in a project called Rio Beyond the Map. And they're looking at Rio de Janeiro's favelas, the really jam-packed, kind of like a ghetto area of the city, where people, 1.5 million Rio residents live there. And that's 1 in every 5 person in the city. So a lot of people aren't aware of the conditions they live in and how cramped it is and exactly what it's like. So what they've done is created this Beyond the Map 360 VR video. You can actually see what it's like to visit the area and explore it. They've begun training people who show you where they are on the map in this amazing journey in VR so that you can get an idea of just exactly what the poverty, the situations, the experience of daily life might be like if you were to be there. So, as a lot of people know, we only hear about these places on the news, and this is different. This takes you down to a day in the life. So, as one of the participants stated, when you're on the map, you don't exist, but we do exist. So this VR project by Google allows us to see exactly what life down in these areas, the favelas in Rio de Janeiro, would be. Well, some people remember on February 27th this year, Elon Musk made an amazing announcement. SpaceX is planning on flying 2 non-astronauts or private citizens on a loop around the moon. Now, this is interesting because really, since 1968, when we first sent people to orbit the moon before landing, there have only been 24 people who have flown to the moon and 12 have walked on its surface. They're all Americans, they're all men. We don't really know who SpaceX is sending yet because they're not linked to Hollywood. They were not recruited, but they came forward and they've paid large sums of money to do this trip. We don't know, but if either of them is a female, it's going to set history, and in any way, they're going to make history, whatever they do. They're going to ride SpaceX's Dragon 2 capsule and its Falcon Heavy rocket. This is a 230-foot high, 40-foot wide rocket, and it has more than 5 million pounds of thrust at liftoff. And the company claims that the Falcon Heavy will be the most powerful operational rocket in the world by a factor of 2. Now, the rocket has not yet been tested. That's going to happen this summer. The Dragon 2 is similar to the Dragon capsule they're using to deliver cargo to the International Space Station, to and from, actually. Looks like they're going to have to get a license from the Federal Aviation Administration to fly it, and they're going to launch from the Kennedy Space Center near Cape Canaveral. They're going to take off from Pad 39A, which was used by the Apollo program for the launches in the late 60s and early 70s as well. So they're hoping that this will happen in late 2018, but as it's noted, that's a very ambitious schedule. They may have to push it back if there's anything less than a flawless performance by months or even years. They will be sending people on pretty much a historic trip. They plan to make this spacecraft loop around the moon. The apex of the journey will be from 300 to 400,000 miles above the Earth, or out from the Earth. The moon is only 240,000 miles. So it's going to be really an interesting flight. They will loop around the moon. They probably won't get incredibly close to it. We don't see any exact cost figures or time schedules. A lot of it still remains in the air. Now, we know that it would be an awful lot of money because even the space tourists of previous times have spent from $20 to $25 million for their flights. A number of people have gone to the International Space Station as private tourists. Dennis Tito in 2001 was the world's first space tourist, and he flew on a Russian Soyuz spacecraft for a price tag of about $20 million. A total of 7 wealthy individuals have become space tourists since that time. So we're looking forward to see what happens and what sort of technology is involved and if he can pull it off. And good luck. And that wraps up our Singularity Watch. Now, the subject tonight, the subject matter, oceans of plastic. I meant this to be something that would give you a lot of thought material. Something that would make you consider exactly what the consequences and unexpected consequences of what we're doing might be. When we use a lot of materials that don't normally exist in nature, and then we dump them in the landfill or the ocean, we know that there's going to be some sort of a repercussion, and we don't always know how it's going to affect nature. And I think a lot of people didn't think about it. I, as a child, watched these huge barges of garbage being dumped out of New York City. They'd haul it out to sea and dump it. And nobody seemed to think a thing about it back then. And we have reached a stage where this sort of thing has simply become accepted. In a lot of places, there's raw sewage flowing right into the waterways. We know this isn't something that we can sustain. We can't justify it. We have to find better ways to do this, and we have those ways. It's like the Flint water crisis. We know exactly how to produce clean drinking water for people, and yet somehow somebody got away with this, poisoning a lot of people with lead, and nobody went to jail. And that's the most amazing thing. It's as if people are pushing the envelope all the time to find out just what they can get away with. But you're killing yourselves. You're killing all of us. And we have to take action. This can't go on. And that's all I can say about it. It cannot go on. Now, our next show I would like to dedicate to batteries and energy storage technologies because it's something that's so important to our lives right now. Particularly when we talk about alternative energy systems, we can generate all sorts of power from the environment around us. The problem is, where do you store it once you've got it, and how do you get it back effectively? So we're going to take a deep, in-depth look at battery technology from its beginning, and it goes back a long, long way, and where we're going today and where it might take us. And I'm going to have my other co-host, Ed Minchow, on the show. And we're both going to present some interesting things about battery technologies and supercapacitors and ultracapacitors and just where we're going to be putting all this energy we generate and what sort of an impact it's going to have on our lives. Not just us, but people all around the world. So battery technologies, and I would probably say energy storage technology is a better way to put it. That's going to be the subject of our next show. I'm going to try and get Eliza repaired and find out exactly what went wrong with her, and we'll go from there too. And after that, I'm going to do the third part of our Mars installment, which has been on hold for quite a while, and there's a long story behind that too. But we have so much material to present. I have people say, wow, you never run out of material. No, we're talking about science and technology and the things we're learning. The learning experience is one of the most valuable and important things in human existence. And there is so much to share. And if only one or two of the ideas that I present get across to you and make you think about the world a little differently or in a positive way, then we've succeeded. We get you to think about the world and your part in it and how it all links together. It's really what being human is about, helping each other, making it easier and better. So remember that scarcity is a myth. We have everything we need to create everything we'll ever need. And also, be ashamed to die until you've won a victory for humanity. Those are very inspiring words to me, and I think that that's something we should all think about. Let's make a victory of our lives. Let's do something positive, something with a net gain, if not for ourselves, and for everybody around us. Because we're the ones who have the ability to make life better. Every one of us, in small measure here and there. And we should be doing that all the time. Love your neighbor. Take care of each other. Make the world better. Make you the world a better or more beautiful place for having lived in it. From our palatial recording studios and our mountaintop lair on a remote volcanic island, I'm Sir Charles Schultz, and this has been Talk Universe. Thank you for listening.